Yeah, okay, thanks, Andrea. So, yeah, so it has become sort of a tradition in the school that every year one of the organizers give a basic, one of the basic courses. So this year it's me, and so this is going to be about an introduction to conformal field theory in 2D. So 2 dimensions is a bit special. So this is an introduction to 2D conformal field theory, or CFT. And my focus will be on, I mean, what I want to arrive at is some, applications to stat-mech and condensed matter physics. So, I mean, this will not be an introduction from the point of view of, say, mathematical physics or string theory. Yeah, so with applications to stat-mech and cond-mat physics. Okay, so and so what I would like to cover ideally, so we'll see if we have enough time, but I would like to start with conformal transformations. I would like to spend quite a lot of time on conformal transformations because, I mean, the whole point of conformal field theory is that it behaves nicely under certain types of geometric transformations. So that's what we will talk about mostly today. Then tomorrow we'll talk about one specific conformal field theory, particularly easy one, which is the free boson or Gaussian free field. We'll see tomorrow that it has several names. Then we'll enter the basic formalism of CFT, general formalism. So there we'll talk a little bit more about the general structure. We'll talk about stress tensor, central charge, and things like that for those of you who have heard these words before. So this will be basic formalism of 2D CFT. This might take 2 lectures, we'll see. So this will be probably 3 + 4. And then in the end, I would like to talk about some important or nice applications to stat-mech and conmat. So that's the plan. But today there will be almost no field theory unless we go very quickly. We'll see. We'll see about the pace. And so for this first lecture, I would like to focus only on conformal mappings. So conformal mapping. Okay. So let's start with the first glimpse of conformal transformations. So what is a conformal transformation? So does any of you know? So who knows what a conformal transformation is? Only 1, 2, 3, 4. Okay, so almost everybody. Okay, good. So what is it? How would you define it? Yes, thanks. So yes, indeed. So it's a transformation. So a conformal transformation is a transformation that preserves angles. So it's a transformation that preserves angles, and what does it not preserve then? I mean, it preserves angles, and what is not preserved typically? Distances, yes, or lengths. So it preserves angles, but not lengths. Okay, so do you have an example of an interesting conformal transformation? some example, some simple example. Z, what's that? What? So where is it coming from? Yeah, but okay, fine, but less trivial than that. Möbius, yeah, okay, so that's already too complicated. No, so some example from you know, daily life. Presumably, I mean, historically, the first example probably of a conformal transformation. No. I mean, how? Imagine you're speaking to, I don't know, your little sister or little brother, and they don't study science, and you want to explain them what is a conformal transformation. What example would you pick? Well, I mean, there, you know, I should have called it conformal map then maybe. So map is the key. Map is the key word, right? Yeah. So that this has a name. It's a stereographic projection. So the most basic example, non-trivial example, of course, apart from the identity or a simple rotation or dilation, would be the stereographic projection, right? So stereographic projection is a transformation that we, you know, that is used in daily life, that you would encounter, and that is non-trivial conformal transformation. Okay, so let's draw a picture. So okay, let's draw a big picture. So you have a sphere like this. That's my sphere. Here's the North Pole, South Pole. Then there's the plane here. That's the plane. Okay, and so let's put a frame. Here's an orthogonal frame. So this is the unit sphere. This is an orthogonal frame. X, Y, Z. And of course, the stereographic projection then works as this. So we start from, if we have a point here on the sphere, a point with coordinates x, y, and z. So it's no, this is the unit sphere. So we have x squared plus y squared plus z squared is 1. And then we just draw a straight line coming from the North Pole to the point, and we look at the intersection in the plane, and we call this x, and this is at some point xy. Okay, so that's and the map from this point xyz to this point here with little x and little y as coordinates. This is the stereographic projection. Now you can easily check that xy can be expressed as 1 over 1 minus z capital X capital Y, and that's cotangent theta over 2 times cosine phi sine phi, where where the theta and phi are coordinates, are the spherical coordinates. So if this is this point, this is angle phi, and this angle here is theta. Okay, is the picture clear? Yes? Good. So how do we see that this is a conformal map? Okay, so I mean we can see it on a if we just draw the picture. So you can see that this sphere if you draw the lines of equal, latitude and longitude like this. So under this map, do you see the difference of colors? It's not clear. Huh? Yes, and like this, is it better? Well, okay, I'm sorry. There's nothing I can do. This choke is just really bad. Okay, so but this then gets mapped to the plane. So the South Pole would be mapped to the origin, and then so these horizontal lines here get mapped to circles, concentric circles around centered on the origin, and then these lines here get mapped to straight lines, like this. Okay, and if you look at the angle here between one of the vertical and horizontal lines on the sphere, it gets mapped to some angle here, say, and you see that this is a right angle, gets mapped to a right angle. So angles are preserved. Okay. Now, if you just want to go a little bit deeper into the formulas, you can write the line element on the sphere. So in spherical coordinates, this is d theta squared plus sine theta squared d phi squared. And you can check that easily that if you write this now in coordinates x and y, this you can rewrite as some coefficient lambda squared times dx squared plus dy squared. So this is the plane here xy. This is the plane xy, and this again, so theta and phi are the spherical coordinates. And the point here is that you see that the line element written in the spherical coordinates here turns out to be proportional to the line element in the Euclidean plane. Okay. So the conclusion that you draw from this is that the metric on the sphere is proportional to the metric on the plane, and therefore it's up to some scaling factor. So the conclusion here is that the metric on the sphere, which has two indices, this is lambda squared times the metric in the plane. And so this is a transform. So this maps. This is a map that preserves the angles. Okay, what is this lambda? Okay, so if you do the calculation, you'll find that this lambda of xy, which is, it has a name, it's called the conformal factor. Conformal factor. So you can compute it in that case, it's very easy, and you'll find that it's 2 over 1 plus x squared plus y squared. And it's not particularly important. Maybe we'll perhaps come back to that later. Okay, any questions at this point? No? Okay. Good. So then we move on now to conformal maps of between planar domains. So conformal maps between planar domain, so just subsets of the plane, two-dimensional planes, planar domains, and we want to make the connection with complex analysis or complex analytic functions. Yes. Questions? No? Okay, so some very basic facts about complex, just complex calculus is complex analysis. So recall that in complex coordinates, if you use complex coordinates for points in the plane, so so a map Z maps to Z plus A, where A is some complex constant. What would that represent as a geometric transformation? So you just take a point and transform it to a point plus some constant. Yes, so this is a translation. This is a translation. Similarly, Z maps to some complex number of modulus 1, so e to the I theta, where theta is real, times Z. What would that be? Yes, so this is a rotation. And finally, if you transform Z into lambda Z, where lambda is real, positive, that's a dilation. Okay. And now the point is that any complex analytic function that has a locally whose derivative does not vanish in some local neighborhood is locally like a composition of these three things. Okay, so now if we look at complex analytic, or what's the synonym for complex analytic? Holomorphic, yes, it's the same thing, right? So we will use both words interchangeably. Will mean the same. So if we look at the complex analytic function on some open subset of the plane of C. So okay, so what we have in mind is something like this. We have the plane, that's the complex plane, C. We are looking at some neighborhood here, some region here. Let's call this U. And we map this with some complex, with some function f that is holomorphic in U. And on top of that, f of z prime vanish. So this then gets mapped to some other domain. So this domain is different from this one. This is now f of u. F of u. So the claim is that this map is conformal. This map, the angles are preserved. Yes. Okay, so how do we see this? How do we see this? Well, it's very easy. So okay, I can. Doesn't take much space, so I can write it here. So why is this? Because so indeed we can expand. We can expand around any point z node. So around z node, some point z node in U, and we'll see that. So we Taylor expand, and then we see that f of z is f of z naught plus z minus z naught f prime of z naught. This f prime we might as well write as modulus of f prime times exponential I times the argument of f prime at the point z naught. And then we recognize a composition of these three things, right? So like this term here would correspond to a local translation. Then this factor, which is real positive, this is dilation, and this phase factor here, that's a rotation. Okay, so the angles are preserved. Any questions? No? Okay, good. So let's have a quick look at some conformal maps. So okay, so one map that is very important for conformal when we go to conformal field theory is the logarithm. Okay, so this is a map. You can view the logarithm as a map that sends the complex plane minus the origin to an infinite cylinder. Here. So the origin would be mapped to minus 2 points at minus infinity here. The infinity of this plane would be mapped to points at plus infinity, and the imaginary part of W here is in this picture is measured modulo 2 pi. Okay, so if you turn around this point, you just turn around the periodic direction of the cylinder. Okay, all clear? So the plane can be conformally mapped to the cylinder with a logarithm. Okay. You can, of course, invert this. So you can look at the exponential map, and of course, given what I just said, then this means that, I mean, you see that it would the exponential would map the infinite cylinder, an infinitely long cylinder of circumference 2 pi, to the complex plane minus the origin. Okay. Questions? No. Okay, but if you notice that if you think of the exponential, but not as a map from the cylinder where you have identified points whose imaginary part differs from by 2 pi, but the full plane, so you look, now I'm looking at the full complex plane, and I don't identify now the points, say, around along the real axis with those along the axis with imaginary part 2 pi. I don't identify them anymore. Then, if I look at this map, what it actually becomes is multiple copies of the plane on top of each other that are connected this way. So you can think of this as branch cuts, or if you prefer, as multiple sheets that are covering the plane with a singularity at the origin. Okay, this is what is called a Riemann surface. Okay. And the formula is the same as before. So this means that you have to be careful and always specify when you write down a formula for a conformal mapping. You have to, be specific about what domain what domain is mapped to. What are the two domains that you are mapping from one another? Yes. Sorry? Uh, I'm not sure what you mean. So, uh, yeah, I don't understand what you mean, sir. Yes. Yes. Um, so, I mean, this line here would get mapped to an infinite line in this direction. I mean, these are different copies of the complex plane, right? So this axis would get mapped to the real axis on one of the copies, right? And then the point 0, it's identified between all the copies. So there's only one 0. And similarly, there's only one infinity. Infinity is also identified between all the copies. Is it clear? Other questions? Yes. Hmm? Well, so this we'll see a bit later. Yes. Of course, yeah. A fundamental question is: does such a map from some domain to another domain, does it always exist? We'll see that later. And there are theorems about that. In particular, the Riemann mapping theorem. We'll talk about this in about 1 hour. Okay, another example that shows up quite often in applications is, for instance, just this map, map z to z squared. So this would map the plane to a double sheeted plane, to two covers of the plane, okay, with a branch cut along the negative axis, for instance. Okay. But again, I can also just look at this map z maps to z squared, and look at it only as a map from, say, a quarter plane like this. So positive real part of and positive imaginary part. So that's not the full plane. It's just a quarter of the plane. It's a domain with a boundary now, with a boundary with a right angle like this. And what I see is that it maps this right angle to a straight line. Okay, so it takes this quarter of a plane and then maps it to the upper half plane. Okay, and it's the same, again, same formula as before. It just now applies to a different domain. Yes. Like the one before. Yeah, so you have to, one way to think of it is that you can think of points being labeled by here a complex coordinate, and on top of that some sort of internal index that tells you on what sheet you are. Okay, and you have to keep track of that. Okay, another example, which I think you mentioned earlier, is do you want to say the name of this one? Yes. Say it louder. Yes. Okay, I say Zhukovsky, but this is just because my Russian is very bad, or inexistent actually. So anyway, so this is also a one map that is particularly useful for applications. So it maps the complex plane minus a disk, minus the unit disk here. So all the points with modulus larger than 1 to the complex plane minus a slit. Turns out for some applications, complex plane minus a slit is much easier to use than the complex plane minus a disk, and we'll see some example of this later. And how does this map work? Well, simply you map z to z plus 1 over z. So why does this work? Because if z has modulus 1, you see that this has a vanishing imaginary part, and so it ends up along this segment here. Okay. questions about this? No? Okay, so I think that's it for my examples. Okay, so then let me give you a quick exercise. So with what we just saw, can you guess the formula for the conformal mapping? Conformal map from this domain. Okay, so exercise. So can you guess the map? So the formula for this map that sends, say, half infinite strip like this. Okay, so this is here I have some points z. This is the real part of z, the imaginary part of z. I'm looking at a strip here that has width, okay, to make the formula easier, let's say that the strip is pi. Okay, so this point here is I pi in the complex plane. And I look at all these points between the real axis and the axis with imaginary part pi. Okay, this is the origin. And I want to map this to the upper half plane. Say. Okay, so this is the upper half plane. So it's the set of all, one notation that we are going to use a lot is for the upper half plane is that h, this h with a double bar, which is kind of, you should think of C with a double bar, which is the full complex plane. So this H with a double bar, this is the upper half plane. This is the set of points Z or W here, such that imaginary part of W is positive. Okay. So what's this map? So the map, we want the map Z maps to W of Z. What is W of Z? So any guesses? So I heard it. Yes. And how do you see that? So the answer indeed is a hyperbolic cosine, so cosh of z. That's the answer. And well, think about it for a few minutes, and then we'll talk. Or maybe think about it over the break, and then we'll quickly talk about it after the break. Unless someone has an argument now for how this works. No. Okay, so think about it and talk about it later. Okay, so indeed, so you asked the right question. So how do we know that such maps exist? Okay, so before we talk about the general theorem, so one thing you can ask is there a recipe for finding such conformal maps, and is there a general formula? And the answer is that in general there is no such formula, except in some particular cases, and one particular case which is always good to know is the case of polygonal domains. So there exists a general formula for polygonal domains. And this formula has a name, Anyone knows the name? Yes. Thank you. So there's a general formula. This is called the Schwarz-Christoffel. Okay, so how does this work? So if you have a some polygonal domain, it can go to infinity. So it can have some pieces that go to infinity. Some polygonal domain like this with internal angles alpha, alpha 1, alpha 2, alpha 3, and so on. So some internal angles alpha j, and these are points z1, z2, z3, and so on in the plane. So this you can always map to the upper half plane. So the different points z and so on, they get mapped to some points along the real axis x1, x2, x3, and so on. So this maps to the upper half plane. And okay, so in fact, the formula doesn't give you the map in this direction. Doesn't give you the map from z to w. Instead, it gives you the inverse. It gives you the map from w. This is w from w to z. So from the upper half plane to this polygonal domain. Okay, and the general formula looks like this. It's not particularly, the formula is not particularly important. It's just good to know that it exists, because for many applications you need an explicit formula, and then it's useful to have this one. So it works as this. So it's the product over all the points at which you have an angle, a corner. Of z minus xj, so zeta minus xj, zeta is a point here. Integrate, so it's a primitive primitive function of this with some exponent that's given by alpha j minus 1. Okay, and you have to fix. Okay, so there are a number of constants that you need to adjust in order to get the right geometry here, but the point is that these exponents, the most important part of this formula is that these exponents are fixed directly by the angles. So you need to adjust this constant a and also the positions of the x's so that it matches. But at least in that case, there exists a general formula. Okay, this formula is not difficult to recover if you forget it. You just have to look locally at what happens. So locally around point, so why does this formula work? Because the point is that around one of the corners, so around a point Cj, what you have is that z minus zj, this will be proportional to w minus xj to the alpha j over pi, right? Because you get this by integrating that. And that's exactly what you need in order to map a corner with an internal angle alpha j. Well, sorry, the other way around. So the upper half plane to a corner with internal angle alpha j. Okay. So that's one general result. We'll see even more general results later. Any questions at this point? Yes? Yeah. So the x is here, and also the overall constant, and and the point at which you start integrating here. These are all parameters with which you can play. You see, this formula does not involve, for instance, of the different sides of this polygon. Well, yeah, but that's, I mean, if you have, if there are lots of segments, a single scale transformation is not enough to fix everything. So then you need to adjust these different points. We'll see. We'll discuss a bit later what exactly is the freedom in choosing these points. Okay. All clear so far? Okay, so conformal maps have been around for a long time, and they have nothing to do with. I mean, initially they had nothing to do with field theory. They've been used in many other contexts, and they are still used far beyond formal field theory. So it's not at all something that is specific to conformal field theory. So let me just very quickly before the break mention some famous applications of these two-dimensional conformal maps. So conformal mapping in some other fields of physics or even engineering. Okay, so one field where these transformations play a particularly important role is electromagnetics or electrostatics for what we are interested in. Okay, so so here I don't want to develop a theory or anything. I just want to give an example. So you're all physicists, graduate students in physics. So presumably at some point in your studies, you've learned how to compute the capacity of a parallel plate capacitor. Let's start with an infinite parallel plate capacitor. So you have two parallel plates like this. There's some wire that brings some charge here, some other wire here. There's some distance between the two plates. Let's call it D. And this one is positively charged. This one is positively charged, so there are some charges here, plus. And this one is negatively charged, minus. Okay, so this one has charge plus Q, this one has charge minus Q. Okay. And the capacitance of this thing, which is defined as the charge that has been the charge that has been accumulated on one of the two planes, divided by the voltage difference. So if there's some voltage difference between the two plates, the capacitance is Q over V. Okay, and do you know the formula for this thing? There's a very famous formula that you learned as undergrads. Okay, so I'm guessing you forgot the formula because you have to remember this annoying factor of epsilon zero, which epsilon naught, which is the vacuum permittivity. So let's get rid of this, and we set vacuum permittivity to 1. Anyway, vacuum permittivity to 1. So in those units, do you know the result? It involves only the area, total area of this plate, and the distance between the two plates. Yes. So this is the area divided by D in those units. Okay, and how do you derive this? You have to use one law that is the name of a famous physicist, or a famous mathematician, actually. Yes. So you use Gauss' law. Now let's just complicate the problem just a little bit, and and this is where conformal invariance becomes suddenly very interesting. So let's imagine that now that, okay, so this is some parallel plate capacitor, but now let's imagine that there's a boundary here. So that you see, this is some very long distance, Lx, say, we have Ly here, this is, Ly is very large, Lx is also very large, but here there's really, there's a boundary. So it can be infinite in the other directions, but here there's a boundary. So the area here would be roughly Lx times Ly. But then the electric field and between the plates is going to be different here near the boundary, and this is going to change the formula for the capacitance. Okay, so there's a formula for this, which is I think due to Maxwell himself. Maxwell was interested in this kind of problems, and you can see, okay, so there's a calculation that you can do that I will give as an exercise, which is the first correction to the formula for the infinite plane, and the first correction happens to be proportional to Ly. This is just because of translation invariance in that direction, and then there's some factor 1 over 2 pi, and then turns out to be proportional to the logarithm of Lx, so the length in that direction, divided by d. And then there may be other subleading corrections. Okay, so this is just some formula that is known in this field that tells you what's the first correction compared to the famous result that you get for the infinite plate case. Okay, and this can be done. This term here you can get easily from a conformal map. So what conformal map do you need to use? Anyone sees this? No, it's not the one from before. I didn't trick you in this way. Okay, so I mean you have to draw a picture. So since everything's translation invariant along the y direction here, we can forget the y direction and turn this into a two-dimensional problem. Okay, so if we have a frame here x, y, z, then we want to draw the projection in the xz plane. No, sorry, xy. No, this is correct. xz plane like this, and so we look at this from the side, and from the side we see this. So we have our two very long plates. They go to infinity on the left. There's a distance d between the two. Okay, this one, the top one, is positively charged. The one below is negatively charged. And so now we end up with a two-dimensional electrostatics problem. And okay, so to compute this, first thing we would need to know is the electromagnetic field profile, or the potential V of x z. So the potential in the plane with those boundary conditions that are set by, so we have two perfect conductors here on the top plate and the bottom plate, and we want to know the electrostatic potential. Okay, and so what do we know about the electrostatic potential? We know that this satisfies the Poisson or Laplace equation. So the Laplacian of V is 0. And now it turns out this behaves nicely under conformal maps. And so the only thing that you need to know is a conformal map from a simpler domain to this one, so that you can actually compute the potential. Okay, so this I will leave as an exercise. It's a very interesting exercise to do, so please have a look and think a bit about it. So first compute v of x and z in that geometry. So that's the first step, and then second, compute this correction, this logarithmic correction to the capacitance. So for this, you will have to do a conformal map. The key ingredient of this calculation is a conformal map from an infinitely long strip of width 2 pi here. So this is an infinitely long strip. This is point minus I pi. This is I pi, and this is x and z, say. So this is some coordinate, let me call it w, in that infinitely long strip. And we need the conformal map from here to here. So let me draw it again. So a conformal map from this domain to this domain here. So let's call zeta the point here. And it turns out, okay, so anyone knows anyone can guess the conformal map that does this, that maps an infinitely long strip of width 2 pi to this geometry here for the Maxwell problem? No. But I mean, if you've never seen it, it's hard to guess. So you can construct it actually as a Schwarz-Christoffel map. It's one particular case. You can play with this formula and you'll find the result. Otherwise, I can just give you the result. So the result turns out to be zeta equals w plus exponential w. Okay, I mean, if you've never seen this, it's hard to guess, but that's the result. So exercise using this, you know, compute the electrostatic potential and then compute this correction. It's a very nice exercise in complex analysis. And with this, let's take the break. Okay, so let's continue. So yeah, okay, so just about this hyperbolic cosine. So how do you see it? So did you think about it? Yes?
You can try, like, one exponent will give you half a plane without, like, with cutoff, like half a circle. The exponent with minus z will give you, like, the half a circle. You can combine them.
Yeah, but if you have two maps, f of z and g of z, it's not obvious at all what f of z plus g of z gives, you know?
Yeah, but then you can just check if they're actually...
Yeah, but okay, but there's a... That, okay, if you want, yes. But you see, then you need to know the answer to be able to check, no? There's a more constructive way of doing it. Yes. No, but I think the key word here is that I had in mind is composition, right? You can compose different conformal maps. Here, this is the key point. So this this half infinite strip here, you can first of all by the exponential map, you can map it to the upper half plane minus minus a half disk of radius 1. Okay, so this you can check. I mean, the infinite strip with an exponential would be mapped to the upper half plane. This is one of the mappings we saw earlier. Now, since it's the left part here, the part with negative real part of z is missing, this means that the interior of this disk is missing. So it gets mapped to the upper half plane minus this disk. But then the upper half plane minus this disk, you can use this Zhukovsky map from earlier, which is just zeta plus 1 over zeta here, this coordinate zeta, and then this gets mapped to the upper half plane. Okay, so in general, it's a good idea if you're willing to construct a specific conformal map from one domain to another. It's a good idea to break it down into smaller steps and steps that you know in order to construct the full map. Okay, so in that case, this hyperbolic cosine, where it really comes from, is as a composition of the exponential and this Zhukovsky map. Okay, so that's what I wanted to say about this example. So now I started to talk just a little bit about applications to engineering. So another one that is very famous is coming from aerodynamics or fluid mechanics. Fluid dynamics, say. And what's that? So, what? Okay. And so this is for the following reason. So imagine you have an airplane. So okay, I'm going to try to draw an airplane. So this is an airplane. It has wings, like this. Okay. This is the pilot. So it has wings, and if you want to calculate, you know, how much force is applied to the wing, knowing, you know, the flow of air around the wing, like this. Well, again, so you can, assuming that the problem is almost translationally invariant in that direction along the wing, you can think of it as a two-dimensional problem of fluid mechanics. So you would have the wing profile like this. This would be the wing profile. Would look like that from the side. Okay, and then you would have your flow of air around it that would do something like that, maybe. So here the heat like this, here it would do that. So you would have air that would go around it like this. And you would like to know what is the force F that is applied on the wing knowing, for instance, the velocity of the fluid flow around. So now it turns out this type of problem can also be solved, at least for the simplest model of these things. This can also be solved by a conformal map. So here what you would have to do, you cannot completely get rid of this hole, but what you can do, the hole that in the plane that corresponds to the wing. But what you can do is map the hole here, the hole that corresponds to the wing, to a segment. This you can always do. You can map it to a segment. Actually, this Zhukovsky map that we talked about earlier, it's doing precisely this for a wing that would look like a cylinder. But such a map always exists, and then when you apply this map, the fluid flow on this side is just straight horizontal lines like that. So there is a conformal map. There always exists a conformal map that does this for you. Okay, so and where does this come? Okay, where does this come from? It's so you have to imagine that you're modeling your fluid flow. So this is a fluid flow in 2D. So there's some velocity field u with components ux, uy. Say this is the plane xy. And this trick that you can apply a conformal map. This works if the fluid is incompressible. So it's a crude model, but in certain cases, this is good enough, at least as a first model. So it has so if the fluid is incompressible, so the divergence of the velocity field is 0, and if it's irrotational, if the flow is irrotational, so there are no how is it called again? No vortices. Thank you. No vortices. Then this trick of doing a conformal map applies. And why is this? Okay, so this is also something that you can do as an exercise, but essentially, if you work in complex coordinate, so if you set uz, which is just the complex coordinate version of this velocity field, so ux plus iuy, then you can check that these two equations here become equivalent to the fact that dz bar uz is 0. In other words, uz is holomorphic, is a holomorphic function of the coordinate x and y. And because it's holomorphic, essentially it transforms nicely under conformal maps. And so if you have a solution in a simple domain where the solution is just completely obvious, it presents itself to you, then you can just conformally map it back to the domain that is really of interest, and then gets some interesting results. Okay, so I will not talk more about this, but it's just yeah. So you have to you have to express the force as an integral of the gradient of the pressure, right? So the pressure you can get from the Euler equations from the incompressible fluid. Then you write the force, and then you write the force in terms of the pressure, and then you will find that the force is given by a contour integral of some form. And yeah, I will not do it now because I mean I would make many mistakes, and that this would take 45 minutes for me to get it right. But I'm happy to do it, to discuss this later. Mm-hmm. Mm-hmm. Yeah, just anything. I mean, this could be completely crazy. It could be a fractal boundary or anything. It exists, yes. Mm-hmm. Yes. Um, yeah, so the result is pretty universal for this type of model. Because in the end, the force is just given in terms of the circulation. So indeed, the precise shape of the wing does not matter. But that's just because it's a particularly crude model, and which breaks down very quickly. So, yeah. But it's this also has this result that the force is just given by the circulation of air around the wing. It also has a name which I forgot. I will find the name for you. The lift, yes. What's the name? Do you know? It's also Zhukovsky. It has two names, and Zhukovsky is one of them. Yeah, and but there's another name attached to it. It's, Zhukovsky and someone else, I think. No. Yes. Thanks. You can find it on Wikipedia. Um, so it's one famous application of this business of conformal maps. Okay. Okay, so that's what I wanted to say about just general applications. Now let's enter a little bit. Let's go a little bit deeper into the theory, and let's explore just a couple of important facts about these conformal maps in 2 dimensions. So the first one, which is the answer to your question, is there always such a map? So the first one, and that's really the fundamental theorem behind many things, that's the Riemann mapping theorem. So the theorem is as follows. It says the following. So if U, so let U be an open, simply connected, and simply connected is important here. I mean, you can adapt the theorem to non-simply connected domains, but then the statement changes a bit. So open, simply connected subset of C, not equal to C itself. So what you should have in mind here is so it could be, you could have the plane C here, and then U could be some domain like this. Okay, some domain that's simply connected, but the theorem also covers the cases where U goes to infinity. So U has a component that goes to infinity. Okay, and actually it also covers the case where, so you have to think of C as being compactified, so including this includes actually the point at infinity. So you can, so simply connected in the complex plane including infinity can also this also includes a situation where you would have all the points around, so where U would be all the points around some region like this, because you could, if you have a contour that a path that goes around this region, then you can close it at infinity. So it's also simply connected in that sense. Okay, so let U be of this form, and you don't have to assume anything about smoothness of the boundary or anything. So what is so this is the assumption, then what is the claim? Then the claim is that then there exists a conformal map then there exists a conformal map from U to the unit disk. Okay, so before I give you an argument for why the theorem holds, let's just consider a very simple example. So the upper half plane. So does the upper half plane satisfy these assumptions? Yes, it does. Okay, so example. Let's take U as H, our upper half plane. Okay, so this is the upper half plane, point Z here. And how can I write this map? Here, okay, so here I'm not gonna make a general argument for why there should be such a map. Just I just want to exhibit the formula. So what's the formula for the map from this upper half plane to the disk? Anyone knows? No. Yes. Okay, so we'll talk about Möbius transformations later, but it's the one that sends. Okay, there are several possibilities, but one is just this. So why? Okay, what does this thing do? This is point W in the unit disk. So what does this thing do? You see that it sends the point I, which would be somewhere here. That's the point I. It sends I to the origin, to 0 here. It sends, and then it sends the real axis to the unit circle. Simply because if z is real, if z is along the real axis here, then the modulus of the numerator is the same as the modulus of the denominator. Therefore, the modulus is 1. Okay, clear? Okay, so that's just one example. So you can always map the upper half plane to the disk. In particular, this also means that because I can always compose conformal maps, it's still a conformal map if I compose them. So if I compose the map that's provided by this theorem with a map, with this map to the unit disk, or to its inverse, say, this also means that I could state the Riemann mapping theorem by saying that there always exists a map to the upper half plane. Okay, doesn't matter whether I specify that this is the disk or the upper half plane. Okay, so let me give you the argument for why the theorem holds. So sketch of proof of the Riemann mapping theorem. And this is a physicist's proof, so it's not. I'm not aiming at mathematical rigor. So the idea is really coming from electrostatics, but I mean it's physics argument, but this is actually how Riemann came up with it. So let's take our domain U. And then what we do is we just fix arbitrarily some point z0 in the domain U. So we fix z0, and then we think of this as a charge, as some charge, which creates an electrostatic potential around it, and we think of the boundary of U, of the domain U, as being a perfect conductor. Okay, so we really think of this as an electrostatic problem. So we fix this, and we look at the potential, electrostatic potential V. Let's call it V of z bar. So I'm using complex coordinates now. Complex coordinate z in this domain. The electrostatic potential is not a holomorphic function, so I have to make its dependence on z and z bar explicit. This is just a rewriting of the fact that it should depend on x and y. And z, I'm using complex coordinate z equals x plus iy. Okay. So we look at the potential that's created by a point-like charge at z0, and this potential should has the following properties. So first of all, it satisfies the Poisson equation. So Laplacian of v is 0 away from the charge. So for z different from z0, the Laplacian is 0. Then, because there is this charge at z0, we have that v of z bar should go as minus, it's a Coulomb potential in 2 dimensions, so it should go as minus logarithm of the distance to this point, and I'm just choosing some normalization so that I have this exponent 2 here. That doesn't matter. I could put any constant here. That's not important. This is when z is close to z naught. Okay. And the boundary condition is that v, because I'm assuming that this is a perfect conductor, so that the potential should be constant. Let's say it vanishes along the boundary of u. Okay. Is that fine? Okay, so this potential has the following looks as follows. So if I look at the equipotentials of V, so the lines along which V is constant, they should look like this, right? So around Z naught, this is really just the logarithm of the distance. So the equipotentials are circles that go around this point, right? And then away from that, they get more and more deformed, and then because the boundary condition is that V is 0 along the boundary, I see that the equipotentials should look something like this. So it's a landscape with a very big peak here, and then it just you get lines that are closer and closer to the boundary of U. Is that clear? And if I draw the electric field lines, so the gradients of the lines of the gradient lines of V, then they are just orthogonal to this, and they go from this point to the boundary. Okay, so the gradient lines would look like this. Okay, so now what important property does this function have? The important property is that it's harmonic, right? So because it's harmonic, harmonicity of V. So this implies that there exists another function V tilde, such that if I define f as V plus I V tilde, so this is a function of x and y, or equivalently of z and z bar. So because it's harmonic, I can construct a V tilde such that V plus I V tilde is actually holomorphic. This is a general fact about harmonic functions, and this V tilde is called the harmonic conjugate, or if you if you want to think in terms of more geometric terms, it's the Hodge dual. Anyway, but so how do we see, as just in a very pedestrian way, how do we see that this thing exists? It's just because we can construct V tilde such that the gradient of V tilde is equal to the gradient of V rotated by 90 degrees. Okay, so you can check that if you construct V tilde so that this equation is satisfied, so that the gradient of V tilde is gradient of v rotated by 90 degrees, then v tilde will also be harmonic, and v plus I v tilde will be holomorphic. This is just saying that any harmonic function can be viewed as the real part of a holomorphic function. Okay, but then the point is that then exponential minus f, so now z is holomorphic, and so then we can look at z maps to exponential minus f of z, and that's the map that we are looking for. So this thing now is the conformal map. That sends the domain U to the unit disk. Let me call it D with double bar. So D is the set of points in complex plane such that z modulus of z is smaller than 1. Is it clear why this is the case? Well, so I mean, we have to look at these properties here. So we've already used this one. So we've used the fact that it's harmonic to construct a holomorphic function. Then let's look at the other two properties. So we know that when z goes to z naught, this behaves as minus logarithm of the distance. Therefore, when we take the exponential, then this map just becomes essentially z minus z naught. So this means that the point z naught gets mapped to the origin. And then the other property tells us that the boundary is mapped along the unit disk. So that's essentially Riemann's mapping theorem. I mean, this proof, of course, is not. I mean, that's good enough for physicists. It's not completely rigorous because you need to justify that such a thing exists. And Riemann himself used something that's called Dirichlet's principle, and then it turned out that this was not rigorous enough, and that's the whole chapter of 19th and 20th century mathematics, but we are not interested in that now. The point is, it's really electrostatics in the end, and playing around with harmonic functions. So as an exercise, you can think of how to modify this theorem if it's not simply connected. So if you have one hole, so don't do multiple holes because then it gets more complicated. But if you have a surface, if you have a domain with only one hole, then essentially you can use a very similar argument. If in fact even a simpler argument. So if you have one domain like this that has a hole like that, so then it's not simply connected anymore. But the point, you can show that there will always be a mapping from this to an annulus. So to an annulus defined as the set of points in the complex plane, so that z modulus of z is between 1 and some number, let's call it r, capital R. So this is the annulus between the circle of radius 1 and the circle of radius r. And this you can also get easily just by thinking about the potential, essentially the electrostatic potential between these two boundaries. Okay. So that's the existence theorem that you were asking about earlier. Yeah. So this is important because it tells you that no matter how complicated the shape you're dealing with is, you can always, there always exists something that allows you to simplify the geometry. So as long as you're dealing with problems which behave well under conformal mappings, such as this one, or such as conformal field theory, as we will see in the next lectures, then it's very useful to know that these things exist. All right, so now let's talk a little bit about a special kind of conformal transformations. These are the Möbius transformations or special conformal transformations, also called global transformations, global conformal transformations. And these are particularly important for the development of conformal field theory. So, I will use the name special conformal transformations, but again, if you prefer to use, it's the same as Möbius or also global special conformal transformations. It's the same thing, it's just different terminology, but also special linear, people also call that special linear. It's all the same. Okay, so what are these things? So these things appear naturally when you ask the question, what are the conformal maps? So when you ask the question, what is the freedom in the choice of this conformal map? So if you look at what we just did for the Riemann mappings theorem, you see that to construct this map from this domain to the unit disk, I had to choose a point, right? I made a choice. I chose one point. I chose those points Z0. I could have chosen any other point, right? And this is the point that gets mapped to the origin in the construction. So this means that if I change this point, I get a different map because it's a different point that gets mapped to the origin. So this means there's some freedom in the choice of this point. That's a two-parameter family of two-parameter family that of how to say this. Yeah, I have to fix. I mean, there are two parameters that with which I can play, and in fact, there's a third one, which is simply a third one that appears in the construction of this v tilde here. You see, because of course v tilde here is defined only up to an additive constant, right? I can add a constant, and then the whole construction will work equally well. So in the end, there's a three-parameter family of maps that all achieve what is promised by the theorem. So this map is not unique. So now, if you start asking questions like, what are the maps? What are all the possible maps from one domain to itself? For instance, from the disk to itself, or we are going to formulate it here as maps from the upper half plane to itself. So the claim then is going to be that all maps, all conformal maps from the upper half plane H, from H to itself. So I really want the map to cover the whole plane, the whole upper half plane, full upper half plane. I don't want to have a map that takes the upper half plane and sends it to a smaller domain, right? I don't want that. I want to cover the full upper half plane. So I want the upper half plane and send it to itself, really. Yes, Vincenzo. Right, so is it clear? So you really want a map from the full upper half plane to itself. So all conformal maps from H to itself are of the form, so this is a point Z, this is a point, again, W, and all the maps are of the form W of Z is A Z plus B over C Z plus D, where A, B, C, and D are real. And on top of that, you see there's some freedom in the normalization here, because if I multiply all four of them by some factor, then obviously this fraction remains the same. So them so that AD minus BC is 1. So that's a strange enough normalization convention, but you will see in 3 minutes that it actually makes sense. And this is a theorem. Okay, so this one I'm not going to give you an argument for this, but it's easy to do. If you're interested, just ask me. You have to use the maximum principle, but it's not very difficult. Okay, so there is a very similar claim statement for the full plane itself. That's the statement for the upper half plane. For the full plane, let's call this theorem bis. So all maps, conformal maps, again, from the full plane, so this time from C to itself, are of the form. So it's the same form. It's also, so Z maps to A Z plus B over C Z plus D. The only difference is that now A, B, C, and D can be complex. And again, there's this funny convention for the normalization that AD minus BC should be 1. Okay? So here, this is a 3-parameter family of maps, because you have 3, there's one constraint, and then there are three free parameters here. I mean, there are 4, but minus 1 constraint. And here, this is a 6-parameter family, 6 real parameter family, or 3 complex parameter family. Again, because there are 4 complex parameters, and then there's 1 constraint. 1 complex constraint, so if you take the real part and imaginary part, that's 2 real constraints. Okay? So, so a question for you. If I take 2 of these maps, 2 of these special conformal transformations, parameters, let's say A1, B1, C1, D1. Okay, so if I have a first map, Z goes to A1, Z plus B1 over C1, Z plus D1, and then I have a second map that maps zeta to A2 zeta plus B2 over C2 zeta plus D2. Then the question for you is, what is the composition of those 2 maps? So what is, okay, so let me call this W, and let me call this, so this is zeta. So what is W of zeta of Z? So you see, okay, so if these parameters are complex, then this is a map from for the full complex plane to itself. This is also a map from the full complex plane to itself. Therefore, the composition is also a map from the plane to itself. And according to the theorem, I should be able to write it as one of these fractions. The question is, what is the fraction? What is the fraction, and how can I express it in terms of the parameters a1, b1, and so on, and a2, b2? So anyone knows? Yes? Yes. Which means? Yes. Thank you. So indeed, so the point is that the composition here is going to be AZ plus B over CZ plus D, where the matrix A, B, C, D is given by the matrix product A1, B1, C1, D1, A2, B2, C2, D2. Okay, you can check this. Just do this as an exercise, as a straightforward calculation. And the point is now you see that the normalization, this normalization condition makes sense because this is just asking that the determinant is 1. Okay, and as a result, the group of special conformal transformations is also called SL2C for the complex plane, or SL2R, so special linear transformations, just because it's isomorphic to the group of 2 by 2 matrices with determinant 1. Okay? Good. And the next thing that I wanted to explain, which is going to be the last for today, is the cross ratio. Let me erase this. Any questions at this point? Or? No? By the way, I mean, if this is too slow and if everyone knows everything already, please just tell me. Hmm? Okay, okay. Because I can go faster. So just tell me. Okay, so last thing I wanted to talk about today is the cross ratio. So this comes about when one thinks about these global conformal transformations or special conformal transformations. And how does this come? How does this come about? So you see, let's focus now on the plane, only on the plane. Forget the upper half plane for now. So let's take the plane, and let's say we have some 3 points, 3 marked points. Three points that we like, that we call Z1, Z2, Z3. Now, because we have this 3 complex parameter family of maps, we can always decide that we apply a global conformal transformation. So there always exists a special conformal transformation. So there always exists such a transformation that maps, say, the point Z2 to the origin. So the f of Z2 is the origin, 0. F of Z1 is the point 1. So this is the origin, this is 1. So these are along the real axis. And then Z3 we can always choose to send to infinity. Okay, so this we send to infinity. And it's a nice conformal transformation, no problem. We can always choose to fix our 3 points in this way. Okay, so how do we do this? Well, I mean, you can just construct it easily. So you want Z. Let's see if I can do this without. No, okay. So if I let me not write it, I'll write it in a second for something else. Okay, so it's clear that this always exists, right? Now. Okay, for up to 3 points we can always do this. But now the natural question that we want to ask next is, What about 4 points? So what about 4 points? So if we have 4 points, and let me just relabel those as Z2, Z3, Z4. So these are the 3 points that I'm going to fix now, and then there's a 4th point, Z1, and this one is not going to be fixed. So if I construct the mapping that sends Z2, Z3, Z4 to 0, 1, and infinity, then the 4th point, Z4, is going to end up somewhere here. Okay, how do I do this? The mapping is this one. So it sends Z3. I may have missed the indices. I'm messed up the indices. I'm sorry about this. So I want to send Z2, Z3, and Z4 to 0. No, sorry, to 1, 0, and infinity. That's the convention I'm using. It's Alfor's convention, so if you don't like it, blame Alfor's for it. Alfor's got the Fields Medal for his work on complex analysis. So the mapping is this then. Okay, it's constructed in this way. So it sends Z3 to 0. It sends Z4 to infinity, and then this is just a normalization, a multiplicative factor, so that it sends Z2 to 1 as claimed. Okay, and now we define. Sorry. Okay, so we define eta, which we are going to call the cross ratio of these 4 points, Z2, Z1, Z1, Z2, Z3, Z4, as f. So this is f of z, as f of z1 under this map. Okay? It's just a definition, and that's called the cross ratio. So now, question. If I take 4 points, and then I use some special conformal transformations, I say these 4 points get mapped to some other to a set of other 4 points. How does the cross ratio change? How does it change? Well, it doesn't change. No, it's obvious from the definition. It's the whole point is that it's an invariant under a special conformal transformation, right? I mean, it's clear from the definition. Why? Because whether you construct the conformal map, the special conformal transformation that that sends the points to 0, 1, and infinity before or after you've done your transformation, it doesn't change anything. Okay, so first important fact, the cross ratio. So this cross ratio eta that's a function of 4 points again. This is an invariant. It's invariant under special conformal transformations. That's the first important fact. There's another important fact that we are not going to use much, but that is useful to know. That's invariant. And that's, okay, so another important fact is that the cross ratio eta is real if and only if, so if and only if So does someone know that? If and only if the 4 points satisfy some property, what's the property? Yes, exactly. So if and only if they are on a circle, they are on the same circle. So I mean, 3 points, of course, can always be on a circle, right? You can always construct a circle that passes through 3 points, but then checking that the 4th point is also on that circle is non-trivial. So if the cross ratio is real, then the 4 points are on a circle. And a circle can also have infinite radius in that context, so it can also be just a straight line. So then they are on the same circle, possibly with infinite radius. Okay, and the last thing, very last thing I want to say, and then we finish, is okay. So we are looking at this cross ratio because it seems to be a natural quantity to consider when we think about those global conformal transformations. But it is instructive, and it will be particularly important for the next lectures, to ask what happens to this quantity, to the cross ratio, what happens to the cross ratio eta under a map, a conformal map that is not a global transformation. Under a conformal map that is not special or global or whatever, or Möbius. Okay, so now what we have in mind is we have our complex plane, our 4 points, z1, z2, z3, z4, and we look at a map that is conformal, but doesn't map to the full plane, for instance. Or let's say it's locally conformal. So around some neighborhood, so I can focus on 4 points that are nearby, 4 points nearby, z1, z2, z3, z4, in some small neighborhood, and then these 4 points get mapped to f of z1, f of z2, f of z3, f of z4. Okay, and now the question I want to ask about this is, I have 4 points, so I can look at their cross ratio. I have 4 points, so I can look at the cross ratio f of z1. So let me call z. Let's say that zj now is z, some central point here, plus epsilon j, and epsilon j is some small vector. Would be epsilon 1. This would be epsilon 2, and so on. Right. So I look at eta of f of z plus epsilon 1, f of z plus epsilon 2. F of z plus epsilon 3, and f of z plus epsilon 4. Okay, and for 4 points that are nearby, it's not difficult to see that this should not be far from the cross ratio of the 4 original points. So it should be approximately equal to the cross ratio of epsilon 1, epsilon 2, epsilon 3, epsilon 4. I mean, the cross ratio is invariant on the translation, so I could also write it as z plus epsilon 1, z plus epsilon 2, and so on, but of course it doesn't matter. Okay, so that's true. That's true to leading order. But if this map here is not a special conformal transformation, then the cross ratio does not need to be exactly invariant. So this is true only to leading order, and if you look at the at the at the corrections, then there's something like there's some quantity that appears. Okay, so it's subleading of order epsilon squared. So epsilon minus epsilon 1 minus epsilon 2 times epsilon 3 minus epsilon 4. That's order epsilon squared, if epsilon is the mean length of these things. And then there is a coefficient here that appears. And let me call this coefficient, I don't know, this of f at point z, say. So this quantity, and then there are some subleading pieces again. So this quantity, this of f, this is something that measures the distortion, the local distortion. So the local difference from a special conformal transformation around the point z, and it shows up in the way that the cross ratio cross ratio changes under a conformal map that is not exactly global or special. Okay. And this, so anyone has, here this thing I just called it distortion, but that's not the conventional name. It has a conventional name, and there's a formula for it. Anyone knows this? Hmm? Shear? No. I mean, it maybe yes, you can call it shear if you want, but it's it's an object that has a special meaning in conformal geometry, and that shows up all the time. That plays a central role in conformal field theory. No one has heard this. It's okay. So let me. So there's a numerical factor 1/6, and then there's a symbol like this, f bracket z, something like that. No one knows this. No, it's not the Poisson bracket. It's not the Poisson bracket. Yes, someone said it. Yes, it's the Schwarzen derivative. So this is the Schwarzen derivative. There's a formula for it. It's given by, so it's the, okay, there's a formula. It's the third derivative of f divided by the first derivative of f minus 3/2 times the second derivative divided by the first derivative squared. Okay, that's just what it is. I mean, there's a formula. You can arrive at this formula directly by looking at how the cross ratio changes. The point is that this is a central object now. This thing here is a central object, the Schwarzen derivative. And it will appear a lot in the next lectures. And that's all I wanted to say for today. Any questions? Yes. I don't have that good one on the top of my head. Apart from saying that it measures how far you are from a global transformation. Um, mm, hmm? Hmm? well, okay. I think it's not completely. Um, it, it cannot be super simple because just because if global transformations they also do something, right? So in particular, if you think, I don't know, of an inversion, or that's pretty something that's pretty radical, no? So it does something to your system, and yet this thing happens to be zero for special conformal transformations. So it measures the distance to a special conformal transformation, but it's yeah, I I don't have a much better way of thinking about it than this. I don't know if someone has some CFT experts in the audience have a better way of thinking about it. Okay, so that's what I wanted to say for today. Any other questions? Well, that's just the definition, right? I mean, that's just the this is how this thing is defined. I could include the factor 6 in the definition, and then it's just normalization convention.
That structure can get some intuition about how it sends circles to ellipses in a way,
Mm,
and that's kind of
yes.
instead of sending circles to circles, it sends like
Yeah. So you mean, okay? So you mean you could take a circle around this point, and this would be sent mapped to an ellipse, or something that is closer to an ellipse than to a circle. Yeah. I mean, okay. Yeah, makes sense. Mhm. Probably. I would have to work it out or find a reference about this, but yes, that would make sense. Yes. Okay, so good. Thanks.